Okay, we're going to start with constraints. So constraints are exactly what they sound like, right? So these are some conditions, some things that limit your motion in some way. Right? So this could be that moving on some surface, that your particles are connected to each other in some way, or it could be something much more complicated. Okay? But these are something they intuitively, the everyday meaning of constraint is actually applicable in classical mechanics. Now, they introduce two kinds of problems. The first one is your coordinates are no longer independent. Now, for example, if you're looking at the rigid body, if you're looking at the particles that form the rigid body, their coordinates are obviously not independent of each other, right? Given the coordinates of a few of them, you know the rest. So they're directly determined. The second one, that these constraints are associated with forces. But we don't know what these forces are. We have to figure these forces out, right? So those forces are going to have an effect on the evolution of our system, but we don't know them a priori. And sometimes they are not going to be easy to figure out. Sometimes they're trivial to figure out. But this is a problem. Now, why this is a problem is going to become apparent in a moment. But I think this one is obvious. Right? Forces are essential to dynamics. So if you don't know the forces, you can't do dynamics. Why is this not? Why is this one the problem? It's not trivial, but it's because of the way we write the equations. The way we write equations, if you actually, if your coordinates are not independent of each other, then you're not going to be able to solve them trivially. But if they are independent, then some solutions are going to be trivial. Now, there are different kinds of constraints. The most important division for us is going to be holonomic and non-holonomic. So what does this mean? So holonomic constraints, there are equations that relate the coordinates to each other. Right? So you can write down some equation, and this is just going to be given all but one of the coordinates. You can find the rest. Right? So I'm going to follow our book's notation here. So these are going to look something like this. Let's say that we have n particles. N particles are going to have n coordinates, and our function is going to look something like this. Yeah. Obviously, it could be more natural that you give these coordinates in another way, but you can always transform them this form by just algebraic manipulation. Yeah. Now, these are sometimes referred as kinematical relations. These relations between the coordinates, and of course, because in this case they are holonomic, these are also called holonomic kinematical relation. Sometimes in some books you are going to see these referred as such, and these actually play an important role. I'll come to this. This notation is not very common. Usually, another letter is used, but this book is skipping that surprisingly. I'm going to spend some time on this, but this is not the general notation. Usually, F is used for an arbitrary function, but it's also used for force, and we're going to see that that's not a choice over here. It's very, very rare. Now, a simple example of such a holonomic critical relation would be, let's say that 1 minus part 2 is L. Okay? Let's say that we have just two particles, and these are their coordinates. The norm of the vector that's connecting these two particles could be fixed, okay, at some L. So this means that the distance between your two particles is fixed, and you're just going to have a holonomic constraint. This is something trivial. In 3 dimensions, of course, it's going to involve square roots and things like that, but these generally not cause any problem. Now, again, I'll just keep going. If you have questions, just interrupt me. It's very hard for me to see your faces, so to get some feedback. So I can't really follow if I'm puzzling you or if you're following. I'll kind of assume you're following, especially since you might have seen these already. But if I'm going too fast, you can't understand what I'm saying, things like that, just interrupt me. I'm happy to slow down. Now, for this non-polynomial constraints, there are a number of ways you can get some constraints in the system that can't be expressed this way. So one of them is that these could be inequalities. So an example of this could be, for example, you have a sphere. Right? So you have some surface. On the surface, you have half sphere, and there's someone sitting on top, and they're sliding. Now, when will they lose contact with the spherical surface? This is a classical problem. I solved this both in freshman year and when I was taking undergraduate classical mechanics course. So you might have seen this. So this is an example of such a constraint. So this prevents you, using some appropriate coordinate system. You could write your constraint this way, and this cannot be expressed in this form. Okay, this is an inequality. You can never take that inequality and turn it into an equation like this. So this will be an example of a non-holonomic constraint. Another class that's going to be important for us. The conditions, your constraints, could involve time derivatives. Okay? So you could be expressing them as an equation, but note that this equation only includes the coordinates. It does not include the time derivatives of the coordinates. If your constraint somehow has time derivatives, for example, your constraint could be that the relative velocity of your two particles is a fixed number. Right? Then you cannot write it in this form either. That will be a non-holonomic constraint. Okay? And these generally they do exist, especially when you're looking at macroscopic situations. But when you're looking at the interaction of point particles, as we normally do, for example, in quantum mechanics and situations like that, like plasma physics, the non-holonomic constraints are not going to be important. Okay? And sometimes you can handle them some way, but you can you just find the coordinates associated with them and so on and so forth. But sometimes it's just there isn't an easy way to handle this, and they're generally going to ignore them. Okay? We're mostly dealing with holonomic constraints, but there are some specific cases where non-holonomic constraints are important, and we're going to handle them. We're not going to try to solve the general case of non-holonomic constraints, which in fact is not possible. So this cannot be done. All right. Else. Now, the example given for this one in the book would be is again. Let me just erase this. That you have some plane, and on that plane you have a disk. So we have a plane, the purely horizontal flat plane, and on that plane there's a disk. And this disk is free to rotate, but it rotates without slipping. Okay? Slipping, and also it can change direction. So it can go, if choose these, for example, as x and y coordinates, it can move in the x direction, it can move in the y direction, it can move in both directions simultaneously. It can also rotate, but it's not going to slip. So how would you express the constraint how would you mathematically express this kind of constraint, that there is no slipping? What's the condition? How do you express not slipping? Do you recall this?
So the motion is only going to do rotation. So it's we can measure it with the circumference of the disk, probably.
But how is this a mathematical expression? Like, for example, can you write something like this? Not involving coordinates, possibly involving its derivatives, but how would you express this in an equation? You know what I'm asking? So that there should be some way to take this description and express the mathematical notation. This is sometimes not trivial. Sometimes it is, sometimes it's not. And it's a skill that you need to have. So here, the velocity of the contact point has to be 0. Okay. So this is one way to do it. The velocity of the contact point. So you write some velocity, and it's going to be 0. And given that, you can write the velocity of the center of mass. You can write the velocity of the top point. So there's going to be some rotational velocity of this, and there's going to be some direction that this is moving. So there's the rotational velocity, and there's the linear velocity of its center of mass. The linear velocity of its center of mass is going to have 2 components, and it's going to be its magnitude is going to be related to its rotational speed, and that rotational speed is going to transform to velocities of each point on this disk. Okay. And the condition that you have to impose is that there's no slipping, so the velocity at the touching point, that point is at rest. Obviously, it's at rest instantaneously, right? So as soon as some rotation occurs, that point is going to start moving, and another point is going to be at rest. This was infinitely confusing to me as a freshman, so maybe it was confusing to you, so maybe you forgot about this, but this is how it works. Right? So if you don't recall this, you need to go back and refresh your mind. So this cannot be turned into a Holmberg constraint. Now, it's not obvious that this cannot be done, right? Especially since if this was one dimension, it could be done, right? This, for example, if you had I don't know, again, this is a classic problem, like a half circle, and you have another circle, a disk. It's just rotating, but now it's essentially one-dimensional motion, right? It's just moving on a line on the inner part of the circle. This can be turned into a Holmberg constraint, because it turns out that if you're at a single differential equation, you can always integrate it. Right? This is something, again, you might recall from your differential equations course. Here, because you're moving in 2 dimensions, and you are going to end up with 4 equations, there are 4 variables, you cannot. You could have, but it's just how the nature behaves. There's no deep mathematical reason for this, but it's not obvious that this actually leads to an non-Holmberg constraint. Sometimes, very similar problems, just because of dimensionality, has very different characters. Right? So this is non-Holmberg. This, in fact, is Lagrangian. But as I said, we're generally going to not deal with non-Holmberg constraints. So the book does spend some time on this, but maybe we'll come back to this when we need. Okay. Now, so these difficulties, how do we handle them? Okay. The coordinates are not independent of each other, and that there are some forces associated with these constraints. So the first one, in the case of Holmberg constraint, there are these. So in the case of Holmberg constraints, you can overcome the first difficulty, the fact that your coordinates are not independent of each other, by using the so-called generalized coordinates. Now, what does this mean? Well, you have some equation, your kinematical relations, and you use this to write down a smaller number of independent variables, and those variables are going to determine your Cartesian coordinates. So implicitly, we're using, when we say coordinates are no longer dependent, what we mean is that the Cartesian coordinates of your particles, of your system, are not independent of each other, and you can express these Cartesian coordinates in terms of some other variables, right? So these generalized coordinates can be something you're familiar. For example, you could just be transforming into spherical polar coordinates. This is something very commonly done when your equations possess a certain symmetry. There are some coordinate systems that suit that symmetry very well, and you're just going to be switching to that coordinates. Now, this is just one way of, and then some of them are just going to be they're not going to be expressed at all. For example, if you're moving on the surface of a sphere, if you try to express this in Cartesian coordinates, you're going to need 3 numbers. But if you're expressing it in spherical coordinates, then you're just going to need 2 numbers, the 2 angles, right? Your r coordinate is not going to change, so it's not going to appear in your equations. The radius of the sphere is going to appear, right? So this could be something as simple as this, but it doesn't have to be. The generalized coordinates can be anything. So they can be something you're familiar, but they don't need to be. Yeah. For example, they could be energy, or some complicated form that depends on the energies of your particles in a complicated way, or Fourier coefficients. So when we look at the oscillating systems, when you have multiple particles, they, for example, if you have just 2 that's connected by some springs, then there are going to be some modes of these particles. There are 2 fundamental modes. They can do this, or they can go, synchronously the other way. And you can actually express your motion in terms of these modes. Those modes are going to have amplitudes, the so-called Fourier amplitudes, right? You can use those as your generalized coordinates. They have nothing to do with the actual coordinates. So these do not have to have dimensions of length or angle or anything like that. They can be anything. Okay? And that's what makes the Lagrangian approach powerful. Right? The equations we are going to write are not just for things that look like coordinates. They're going to be valid for generalized coordinates. And because of this, we are going to be able to handle many more problems more easily and more naturally. Because a lot of problems are going to fit into these situations where the generalized coordinates are going to be things that do not look like coordinates at all, but the Lagrangian approach is going to handle them appropriately, whereas the Newtonian approach is going to have immense difficulty, right? For that, you need the acceleration, you need the velocity and things like that. But now, the generalized velocity does not look like velocity. F equals ma is not going to hold because the acceleration doesn't look like acceleration, and there is no associated mass. Okay? But we are also going to generalize the concept of force, and we're going to do it today. So hopefully all of this is going to become clear. Now, I want to carry out a couple more definitions. If we have n particles, so we are going to have n position or n coordinates. And these are named. We say we have 3 n degrees of freedom. Okay, if we have n particles, I should say n free particles, right, uninteracting. Obviously, this is not just the case for free particles. There could be some external forces or independent. Yeah, that's what it's independent. So there could be stuff acting on them, but the stuff is acting on them independent of each other. Then they're going to have these n coordinates. Each of these coordinates are 3-dimensional vectors. So we're going to have 3 n numbers that describe our situation. We see we have 3 n degrees of freedom. If we have k we have k moment constraints, then we're going to have k kinematic relations. Well, not really, but we'll have a number of kinematic relations, and then the degree of freedoms is going to be 3n minus k. Okay? And we're going to have 3n minus k we will have 3n minus k generalized coordinates. So we are going to denote this as, Q1, Q2, Q3, Q3n minus k. So Q are going to be our generalized coordinates. That's the general notation used for coordinates, and we're going to just stick to it. Now we can express this. Again, I'm going to have to recycle this. We write this in a form that our original coordinate is actually going to be a function of this Q1, Q2, Q3, Q3n minus k, and then possibly time. Okay? So the relationship between the generalized coordinates and the original coordinates could involve time. Right? This doesn't make things any different. It makes things sometimes a bit harder, but doesn't really matter. There and down to kind of these. So these are called our transformation equations. So when we say that the transformation equations for generalized coordinates, we are referring to these. Sometimes you'll see the opposite, Q's expressed in terms of R as transformation equations. I don't think it matters too much, but it's just there's no consensus on what to call transformation equations. Now, one thing to note is that so because these not only these are not necessarily coordinates, they are not going to form vectors, right? So your original Cartesian coordinates, they form vectors, right? I just wrote one vector equation, or in fact 3 equations. This stands for 3 independent equations: the x component, y component, and z component. And hence, I ended up writing n vector equations corresponding to 3n scalar equations. You can't do the same for the Q, right? So this is important. Now, this sometimes upsets people because the vector equations are, of course, very powerful, right? You write a vector equation, then it becomes independent of the coordinate system, but this is automatically built in. Like when you're using generalized coordinates, again, you're going to be able to write down expressions that do not depend on your coordinate system. In fact, you're losing your coordinate system. Okay? So this is sometimes a concern for people that you're losing something. You are actually not losing anything. And I'll try to demonstrate this, but it is not going to be too important for us. But when you're dealing with things like general relativity, then sometimes people get concerned about this. There's no need to be concerned. Okay. Now let's look at. Are there any questions? Am I going too fast, or is it too familiar? Am I going too slow? Anything? Okay. So let's get the second difficulty. That we have some associated forces, but we don't know what these are. So I'm going to erase this, but we can keep those in mind. Is that a problem? So far we had a set of equations, the kinetical relations that relate the coordinates to each other, and the transformation equations that relate the coordinates to the generalized coordinates. And so I will refer to those. Now, how could a constraint have some associated force? Right? So this is one thing. For example, actually, just think about it. For example, if you have 2 particles that are fixed at the distance, can you actually have a force that's associated with this? How would you go about constructing that force? Did you do this in the undergraduate classical mechanics course? Now, it turns out you can't really write down the force because that's kind of a limiting case. Okay? But we can write a potential, and that potential is going to have a tunable parameter, and we can tune that parameter, and when we take it to a limit, it's going to give us our constraint. Okay? So when we say that there is going to be a force associated with the constraint, we are kind of lying. It's not a real force, because in some sense it's going to be some limit of a force, but at the same time, who cares, right? Of course, there are no infinities in physics, so you just make something very large or something very small, so it's going to work. Now, one constraint force that you might be familiar with is the normal force, right? So if you're moving on a surface, you can't enter the surface, and if you're just resting on the surface, the normal force is going to be something that's compensating everything else. Like if you're sitting on a flat surface and you're not getting into this, the normal force is going to be opposing gravity, right? But that could be additional forces. You could be pulling on this, pushing on this, but so normal force is going to compensate everything else. So in that case, it's familiar. Unfortunately, that's actually a non-holonomic constraint, so I'm not going to use that example. I will, however, use this. So the fixed distance. Now I'm going to have one-dimensional system with two particles. So because this is two particles, one-dimensional, we just have x1 and x2 as our coordinates, as our original coordinates. Now I'm going to have a potential x2, and this is going to have this form. A raised square. Okay. X1 minus x2 is L squared. Can you read this? So this is a half A, and in parentheses, x1 minus x2 minus L squared. What's this? What's the system? It's one-dimensional.
Kind of
I have a
spring.
particle here, another here. Okay, go ahead.
Could it be a spring system?
Is this a spring system? Is it spring?
Could it be?
What do you think? Elif Bakkaloğlu, what do you think? Is this a spring system?
I'm not sure, hocam.
Okay, what do you think though? I'm not sure, doesn't provide what you're thinking. So how does the potential for a spring system look like? What does it look like?
1/2 K.
No, Shahin, not you.
Oh, okay.
It look like that.
It looks like this. So is it a spring then? Ertuğrul, what do you think? Ertuğrul Karamanlı.
I think a spring system would have K, the spring constant. So I don't think this is a spring system.
So you're saying that because I didn't use the letter K, it's not a spring?
I mean,
Letters are arbitrary.
yeah, but L here is probably the distance, not distance, the
But I have an A.
length.
Let's make this a K. Is it a spring system now?
Could be, I guess. I
Could
don't
be.
really know.
So for a single mass on a single spring, the potential energy is a half kx squared. Right? This is physics, 101, not even 105. What's this x?
The kind of displacement from the rest position.
This is the distance from the equilibrium point. Right? You're moving on one dimension. This is distance from equilibrium point. So this is a restoring force. It doesn't matter which direction you go. Your potential energy is going to go up as you get farther from the equilibrium point. This is the same thing, except the center of mass motion doesn't matter. Right? It's the relative distance, x1 minus x2, that matters. So when that x1 minus x2 is equal to L, your potential energy is 0. When your x1 minus x2 is different from L, whether it's smaller or larger, your potential energy is going to go up. It's the same situation as here, except instead of x, we have this. And the physical meaning of this is that there is an equilibrium distance between these two. And if you deviate from this equilibrium distance, then you're going to have a restoring force. The restoring force is just going to be proportional to the distance, right? This leads to a force x this is going to lead to something similar. Okay, now how do you solve this problem? How do you solve a problem like this? Given this potential, not using the techniques we have, not using techniques that we are going to learn. You might already know them, of course. You might already be familiar with Lagrangian Hamiltonian mechanics. But how will you solve this? Newton's laws. You have a potential. What does potential give you?
We get the derivative of the potential, we will get the force. And if we get partial derivatives, if we consider two separate systems, the reference system of x1 and x2, we will get two separate differential equations, and then we will try to solve for each particle.
You'll try to solve those. Okay.
I
Did you
assume.
follow that? Nisharin, did you follow what Shahin was saying?
Yes, hocam.
So do you agree?
Well, in this case, yeah, we will do that, but rather than that, I'm not sure what.
So he said that you take the derivative of the potential. Derivative with respect to what?
With time, but
No.
he said with time.
With
So
positions.
But if you take the derivative of potential with respect to time, you don't get force. What do you take the derivative with respect to? The coordinates. Right? It's the gradient of the potential. In fact, minus gradient of potential, the way we usually define potential, that leads to force. Okay? Or potential energy, I should say. So here, this is going to, if you take the derivative of this with respect to your x1 and x2, that's going to give you the force that's felt by the particle 1 or particle 2. Now, okay, so this is one approach, and you could do it that way, but if you try to do it that way, you're going to encounter some difficulties. That is not really going to work. Okay? You're going to end up with some equations that you're going to have some difficulty solving. They can be solved. They can be solved for sure, but there is another way. And I already gave you hints of how to approach this problem. And this is something we are going to do again when we look at the Kepler problem, the central force over our potential. So what was the magic words that I used? Do you recall when I was referring to
Modes?
There are modes, but no, that's what I'm talking about. So this is just going to have one mode. They're going to just oscillate this way. But you need to divide the motion into two parts. The relative motion that has the coordinate this. And what's the other part of the motion? Ecem, do you remember? Did you see this in classical mechanics 1?
I guess, Hocam, I couldn't remember it right now.
Okay. So when you have the gravitational two-body problem, you do something very similar. You look at the relative motion, which gives Kepler's equation and so on and so forth. Plus, there is the motion of the center of mass. And so you have to divide this into two. So that's going to be m1, x1, m2, x2, y5, m2. So it turns out using these general coordinates is going to be very beneficial. This one just does linear motion. So this potential is completely internal. There are no external forces on my system. So the center of mass is going to either remain at rest or move with constant velocity. The motion of this coordinate is trivial. This is plus. The motion of this is going to be a little bit different. Okay? So it's going to be relative motion, and I have in fact the answer here. This x1 minus x2 is going to be L plus B by A sine And that mu is the so-called reduced mass. And that A is what's given over here. And this E is energy. So it's the kinetic energy of the particles. Particles plus the potential energy arising from this interaction. Now, if you look at this, these are going to be some oscillations. So there's an equilibrium value L, and around this there are some oscillations, right? So as time goes on, you're just going to oscillate around L, equilibrium point. The relative motion is going to have an oscillatory behavior. Now, what's interesting here is that when I change A, as you make A larger and larger, as A in fact goes to infinity, the frequency of the oscillations is going to increase. The frequency is going to explode as well. See, but the amplitude is going to die. Right? Here A is in the denominator. The amplitude is going to go to 0. It's a little bit troublesome, perhaps, that the frequency is going to infinity, but the amplitude is going to die, which means that this is going to be fixed at L, and that's your constraint. Right? So if you want to just get two particles fixed at a distance, this is what you can do. Obviously, this can be generalized. So we can make this three-dimensional and so on and so forth. It's a little bit more involved, but the generalization is trivial. And then you take this, and then you just make your A arbitrarily large. And that's going to give you a constraint. And now, because you start with the potential, you know exactly what the associated force is going to be. It's in fact going to be this A times the derivative distance of these two minus L. And so the force is going to vanish when the derivative distance is L, but otherwise it's going to be something arbitrarily large. Ideally, something infinite, which means that if you try to move away from this equilibrium distance L, then you can't. There's an infinite force actually preventing. Right? So this is one example how there could be an associated force with some polynomial constraint. There are other examples where how we can restrain something to a plane or a surface or something like that, but I'm not going to go into details of this. It's not completely crazy to think that if you have a constraint, there's going to be some force associated with this. This was the point where I did this. Now,
John, may I ask something?
yeah.
What is the energy? I mean, so we have the potential energy U, but
Right.
is it the same
Plus the
thing?
kinetic energy. So
Okay.
the half m1 x1 dot squared plus the same thing with the second particle.
Okay, so during the course, we are going to see some methods to solve the equation to obtain the relative motion, right? So because I'm not familiar right now, so I'm just scared. So
Okay, this excellent. Thank you very much.
okay.
So then next lecture I'll prepare and show how this is solved,
Okay.
because you need to know this. Okay.
Okay.
I will assume when we are doing the Kepler problem, gravitational two-body problem, I will kind of assume you're familiar with this. So it's best if we go over this. But so next time we'll start by solving this problem. I don't have anything prepared right now, and I don't want to deviate too much. But yeah, let's just do this. I'll also try to find a good resource. I suspect this must be in Marion. So is that what you used for undergraduate classical mechanics? Was it Marion?
No, it wasn't Marion.
Okay.
But I couldn't recall the author's name right now.
That's fine. We use Marion. So, and I seem to recall that we did this. So that's why I say, but I'll find also a resource and I'll try to send before the lecture so you'll have a look. But also we'll just at the beginning of the next lecture, just do this separation to center of mass plus the relative motion.
Okay, John, thank you
Because
so much.
we are going to need this for the two-body motion. No, thank you. Thank you. I really appreciate it.
Well, may I ask another question about
Yeah,
this
of course.
problem? So were we able to define the kinetic energy in terms of the reduced mass and central mass as well?
Yes, you can. Yes.
So instead of 1/2 like mx1 dot squared, instead of that, can we write 1/2 mu x central mass dot squared? But in that
So-
sense, central mass, does it move?
So yes, I will erase this, but hopefully you recall the system. So instead of so this is what we all know. And this is also equal to, and this is the total mass.
Mhm.
This is the reduced mass. And that's the relative motion, relative velocity. Yeah.
Okay.
So you just need to plug numbers in and see that this is in fact correct. This is probably not obvious, but does work.
Yeah, so considering that the problem was considering the vibration of the two particles or two masses, I was assuming the central mass will have no velocity because it remains.
Yeah,
Yeah.
the expression assumes that you are in the center of mass frame.
Okay, great, thanks.
Anything else? So if you have, in fact, writing it this way is not good. You should just write this part, because if you write it this way and somehow you are not in the center of mass frame, then you're going to end up with some superfluous energy. But we will do this formally next week. Okay. This. So we have some forces associated with them, and we also want to switch to some generalized coordinates that we can use to simplify and interpret our equations. Now, this difficulty, that the fact that we don't know these forces, is kind of ignored. Okay? So we say that the forces has some certain properties, and if they don't have these properties, then we say that okay, we're not dealing with the system. Okay, and if they have these properties, then we can deal with them. And this is a little bit confusing. This is one of the things that makes D'Alembert's principle confusing. So there are different formulations of this, and I'm going to use the book's formulation, but that's not the only one. So we're going to say that D'Alembert's principle is some equation, but you could also express this as a hypothesis. You could also say that we have a mechanical system, the kind of systems that we deal with, and for the mechanical system, by definition, this relationship holds. Okay? So this is another way of expressing D'Alembert's principle, but yeah, it's this is a little bit abstract right now, and we're going to make this more concrete in a moment. I'll repeat this argument, how to state D'Alembert's principle in two different ways. Now we're going to, so if marker is dying on me. So if I is the force on ith particle, and we're going to separate this into two. Our Fi is going to be Fi applied with this little a subscript in the superscript, sorry, for applied force plus the force that's coming from the constraint. So this is the applied force. And this is going to be the constraint force. Okay. Now, we consider a system in equilibrium And as a consequence of this, all Phi's should vanish. Right? So the total force on each particle should vanish separately. Now we are going to define the so-called virtual displacement. Yes. So this is a concept. So it's a displacement. It's a change in the coordinates. These particles are original Cartesian coordinates that is consistent with the forces and constraints on the system. Yeah. Don't worry about the forces part. It's mostly consistent with the constraints. Okay? So this is a small change. This is a lowercase Greek delta here. Small change in your original coordinates, consistent with the kinematical relations. Recall that those kinematical relations are what defines our holonomic constraints. Well, this is perhaps if you're, for example, if you have a bead on a wire, that you just move the bead a little bit on the wire. It could be something like this. So obviously, in that case, because you have these kinematical relations, these constraints, your coordinates are not independent of each other. So not every small displacement is going to have independent components. Right? So this is what we have. Now, for this virtual displacement, we are going to have the virtual work. Okay? This is the work done over the virtual displacement. These are just definitions. Okay, I just want to use these terms, and so we're going to just use what is already established. Now, let's write these down. So I want to keep this. I will rewrite it. My Fi is Fi applied plus small f, and I'm going to have some total work done on my system, which is of course just the force dot product with this displacement. Okay. Can you actually read what I'm writing? Is it legible? So this is just what I've written before. My force has two parts, the applied force and the constraint force. And this is the total work done, the virtual work. So virtual work, all this. It's just a dot product of this total force times the virtual displacement. And just substituting this in, I'm going to have Fi applied dot delta Ri plus small fi, the constraint force dot delta Ri. This is nothing. Okay. Now we now assume that this is 0. This just vanishes. Okay. Now this might be something that sounds overly constraining, that's over limiting, that we are just looking at only special kinds of constraints, but this is not so, right? So a lot of the interesting constraints that we are going to be interested in is going to be of this form, where if your displacement is consistent with the constant with the constraints, then they're just going to vanish. Obviously, this is going to vanish for the whole constraints. The whole constraints restrict this in a way that you're going to be consistent with the constraint forces, so that's just going to go away. One particular class that's perhaps important is that this doesn't allow you to handle frictional forces. Okay? So the frictional force for the frictional forces, this virtual work is not going to be zero. Right? The frictional forces cannot be written as Solomon constraints, and so we are not going to be able to handle those this way. But we're going to come back to it, and we're going to see how friction and dissipation will actually be incorporated in our approach. Right? So this might look something very, very limiting. It's not. Just take my word for it, and it's going to make our lives not just easy, but actually possible. So another way to put the Lambert's principle is saying that a mechanical system, or the kind of systems where the equations that we are going to drive are valid for, is the case where this vanishes. And so you define a mechanical system, a system such that the virtual work by the constraint forces vanishes, and then you proceed that for a mechanical system, you show that the Lagrange equations actually hold. So this is one way to put Lambert's principle. Another way that our book uses is, I know I'm over time, I'll just actually, so if this is true, then I've got applied delta or I is zero, right? So because the total virtual work has to be zero by equilibrium, because this Fi is zero, the work done by itself must be zero. This is of course trivial, but then if this part is zero, then the other part must also be zero. Okay? This is like something perhaps very trivial, but this valid only for a special class of systems. Now I'm going to take